Black holes have always been understood as the places where dead stars become the grim reapers of the universe. They are famous as places where nothing can escape, not even light. So what is inside black holes that makes them so special? What would happen if we fell into a black hole? All matter in the universe warps by time, creating gravity. This is relatively easy to understand in Einstein's theory of relativity. What is easy to grasp is Newton's third law of motion, which states that every action has an opposite reaction. Thanks to these two laws, humanity understood they should travel in space. They can use a strong enough force to lift a spaceship out of Earth's gravity and then use the reaction to move through infinite space. However, these concepts become meaningless when facing a black hole. Black holes are the graves of supermassive stars whose gravity is also massive. Around black holes, gravity is like an eternal deep pit that can make anything fall in and not escape. This is where even light cannot escape. This is when the concept of the event horizon starts to make sense. The event horizon is where black holes hand out one-way tickets to any object wanting to reach them. Once an object crosses the event horizon, it gets a one-way ticket straight into the black hole along its predetermined path. Why is this so? The event horizon can be understood as the edge of a waterfall. Before reaching the waterfall's crest, boats can still row back upstream and escape the freefall in front. Though extremely tiring, this escape is still possible. But once past the waterfall's mouth, one will freefall and cannot turn back. If we replace the waterfall with spine, we see black holes are no different than waterfalls. Once we go past the event horizon, we freefall into the black hole with no return, even if we try our hardest to row against it. At this point, we may think of creating a propulsion force to fly out of the black hole. But this is meaningless. The black hole's gravity warps speed, not like the waterfall's spatial flow. Space cannot move through itself. The spin and warp will warp us too, since we are also part of spin. This phenomenon is called spaghettification. Our bodies get stretched lengthwise and compressed widthwise into long, thin forms like spaghetti. The stretching is so strong that nothing can resist it. Moreover, it orients our bodies to a single central point, changing our volume over time. In that state, any propulsion force we create would place atomic energy into the black hole, making it heavier, pull us in faster rather than pulling us out. Our accelerating fall into the black hole despite our hardest efforts to escape sounds like quicksand. But that is the nature of gravity, one of the most fundamental forces in relativity. So as soon as scientists understood how black holes form and their basic properties, they immediately grasped why black holes are only one-way tickets. This is not the only strange occurrence in black holes. One of the most noticeable traits of black holes are the bright disk and a massive gravity matter that's trapped orbiting it. However, things are much different around black holes. When matter contacts a black hole's gravitational field, it gets drawn in like any other celestial body. However, the extreme gravitational field warps, compresses and draws the matter into the black hole's center, causing intense friction and heating. The matter glows brightly, becoming huge bright spots in space. This disk looks magnificent, seemingly a masterpiece of creation. However, it is a hell-contained material heated to extreme temperatures and compressed towards the black hole's core. But this is not the only strange occurrence. Light moves through space-time like a submarine through tunnels. And when space-time tunnels are warped, the light submarine must also take a curved path. However, unlike underground tunnels, the curved path around black holes causes light to go from one side of the black hole to the other side in a flash. Everything around black holes acts as a massive mirror, creating heavily distorted images. If we fell into a black hole, we would see twisted reflections of ourselves everywhere around us. Light from space reflecting back to us as walked by the black hole's gravitational field and curved space-time, bouncing back to us. We would be an extremely confusing space where we see ourselves everywhere in convoluted reflections. However, we are not the only ones suffering these near black holes. Light, and any waves of wavelengths, Shorter wavelengths mean stronger light. Longer wavelengths mean weaker light. As light travels infinite space, it weakens redshift into longer wavelengths. We can understand this redshift as a cosmic Doppler effect. When a sound source passes by us, the sounds shift down in frequency or pitch. Redshifting causes the color spectrum to shift from blue purple short wavelengths to long red wavelengths. This effect is called redshifting, referring to the reddening color shift. How does this relate to black holes? With their immense gravity, black holes warp and stretch, splitting to extremes, redshifting the light reflected from matter around it. Like how moving sound sources, Doppler shifts down in frequency as they move away. Light traveling through stretched space-time also redshifts as it approaches black holes. As we fall into a black hole, outsiders won't see us get sucked straight into the massive void. Instead, they'll see us frozen in place and moving and unresponding, as if dead. Over time, our image will steadily redshift under the redshift effect until all color disappears and we fade to black, literally becoming part of the black void of our eyes. Words return to the gun when shot out of it. If this happened, we may witness someone enter a black hole, only to get shot back out by its time reversal. And if time stops, does the spaghettification process also stop, or does time keep infinitely stretching? How can we tell time is passing if it keeps infinitely expanding? With infinite distance between feet and head, how can signals from feet reach the head? We may become frozen in time as it infinitely stretches. We may die instantly from spaghettification, or we may see the future. We may not perceive anything before immediately becoming part of the black hole. We can only speculate based on what we know of theoretical and experimental physics. With the two leading theories of everything, relativity and quantum mechanics, so far we have understood how abstract spying is around black holes. Black holes are extremely perplexing phenomena. They challenge not just physicists and mathematicians, but all of us less intelligent than scholars to be constantly curious about them. So will this story about them mainly involve gravity? Or do we have another story left to tell about them? Perhaps we have one more story to tell, which will be the next part in the black hole story. If you liked this video, don't forget to like, subscribe to us, and click the notification bell to not miss any future videos. Thank you for listening and see you next time. Bye.